Good afternoon, everyone. This is the session 4 from the playlist of IIT JEE Advanced Part 2. The topic is motion of a charged particle, and this topic is from the chapter of electric charges and fields. And today I have taken one question which was asked in the JEE examination in 1988. The question here is: a thin ring of radius capital R carries a uniformly charged capital Q, a uniformly distributed charge capital Q. A point charge minus Q is placed on the axis of the ring at a distance x from the center of the ring and released from the rest. Prove that the motion of this charged particle is simple harmonic along the axis of the ring, and at the same time we have to find the frequency of oscillation. So in order to save the time, I have already drawn here one figure. So in this figure you can see that I have drawn one ring. Let us, you can denote this ring as B, C, D and like E. So B, C, D, E, this is the ring, and O is the center of this ring, and a charge minus Q is placed on the axis of this ring. This point, I have depicted this point as A, and the distance of this negatively charged particle is x from the center of the ring, and the radius of this ring is capital R. So we have to find the nature of the motion of this charge minus Q when it is released from rest along the axis of this ring, and we have to show whether this motion is simple harmonic or not. So for this purpose, for solving this question, let us first of all consider a small differential charge element on the surface of the ring. Differential charge element, say dq. Okay, let's consider a differential charge element dq on the surface of the ring at any point. You can consider that element at any point on the surface of the ring. So I have taken that that differential charge element dq at this point B of the ring. So now this is a positive charge and this is a negative charge, so there will be an electrostatic force of attraction between them. So the electrostatic force of attraction, let us say because of this differential charge element dq, let us say I am just taking it as F, and this is equal to 1 by 4 pi epsilon naught minus q dq upon the distance between these two charges. So the distance between these two charges will be equal to what? We will use the Pythagoras theorem. So OB square plus OA square is equal to AB square. So AB square will be equal to R square plus X square. So this is equal to R square plus X square. And here in this formula, I have used this 1 by 4 pi epsilon naught. Here epsilon naught, actually the formula is epsilon. That is where epsilon is equal to epsilon naught into epsilon r, where epsilon r is the relative permittivity of a medium, epsilon is the permittivity of the medium, and epsilon naught is the permittivity of free space. Now since we have considering this configuration of charge, or this system of charge to be existing in the free space, therefore I will be writing this formula as 1 by 4 pi epsilon naught, because the relative permittivity of the free space is 1. So epsilon becomes equal to epsilon naught. So we are considering this system of charges to be existing in the free space. So and this force, the direction of this force will be along AB. This is an attractive electrostatic force, and the direction of this force will be as indicated by this arrow. Now, I have considered the that this force is making an angle theta with the axis of this ring here. So cos theta, if it is making an angle theta with the axis of the ring, then cos theta will be equal to base upon this hypotenuse. So base is x, hypotenuse is what? Under root of r square plus x square. Because this is the radius of the ring, this is x, so this will be equal to under root of r square plus x square. So base is x and the hypotenuse is equal to under root r square plus x square. So cos theta is, the value of the cos theta is equal to x upon under root r square plus x square. Now, this is the magnitude of the force along this direction, that is along AB. Now I have to find the component of this force along the axis of the ring. The component of the force this electrostatic force along the axis of the ring. Along the axis of the ring, this will be, say, this is equal to D. This will be equal to the component of force along the axis of the ring. I am just taking it as dfx, let us say. So dfx, this will be equal to what? This force along the along AB is equal to, is given by this formula. So the component of the force along the axis of the ring, which I have taken as dfx, so this will be equal to base upon hypotenuse. So this will be equal to f cos theta. Now f cos theta, the value of this f is minus q dq divided by 4 pi epsilon naught r square plus x square into cos theta, and this, the direction of this force will be along will be from A to O. That is, the force, this electrostatic force will be directed towards the center of the ring. So the component of the force along the axis of the ring, which I have taken as this as a dfx, so this is equal to minus dq, minus q into dq, which dq is what? It is the differential charge element which is placed at this point B, divided by 4 pi epsilon naught in bracket r square plus x square into cos theta. Now, so dfx will be equal to, now I will be substituting the value of cos theta as x upon under root r square plus x square, under root r square plus x. So this will be equal to minus q dq x, okay, because cos theta will be x divided by under root r square plus x square, and this will be equal to 4 pi epsilon naught, and this is r square plus x square, and this is equal to r square plus x square under root. So this will be equal to r square plus x square 3 by 2, because under root is equal to, this under root will be, can also be written as 1 by 2. So this will be equal to x divided by in bracket r square plus x square to the power 1 by 2. So this will be equal to r square plus x square in bracket to the power 3 by 2. So this is the value of the force, electrostatic force along the axis of the ring towards the center of the ring. So now this is the force due to this this differential charge element dq. So if I integrate this equation, I will be getting See here 4 pi epsilon naught q x, this bracket में जो है आपका r square plus x square to the power 3/2, all these are constants. So minus qx divided by 4 pi epsilon naught r square plus x square 3/2. This is a constant minus qx 4 pi epsilon naught in bracket r square plus x square to the power 3/2, and I will be integrating this dq. So finally what I will be getting is, that is let us say fx, that is the force, the electrostatic force along the axis of the ring towards the center, it will be equal to minus q, capital Q, the integration, because see here this is a thin ring which carries a uniformly distributed charge q. So this integration of dq will be equal to q minus small q, capital Q, x divided by 4 pi epsilon naught r square plus x square to the power 3/2. ठीक है. So now the force is equal to mass into acceleration. So I have substituted the value of this force as mass into acceleration. This is equal to minus q divided by 4 pi epsilon naught r square plus x square to the power 3/2 into x. Okay. Now here in this question it is given that x is very small in comparison to the radius of the ring. So if it is so, then this x can be neglected, or we can write x is equal to 0. So this equation will get converted into minus q divided by 4 pi epsilon naught this r square, since x is equal to, since we are taking x as 0 because x is very less in comparison to this radius of this ring. So this will become equal to this r square to the power 3/2. This will equal to r cube into x. Or we can simply say that the acceleration will be equal to minus q divided by 4 pi epsilon naught m r cube into x. So it implies that now we know that I think every one of you must have studied while under the topic of oscillations. While studying the chapter or the topic of oscillations, you must have studied that the acceleration of a particle executing simple harmonic motion is given by a plus omega square y, which is equal to 0, where a is the acceleration of the particle executing simple harmonic motion, omega is the angular velocity, which is given by 2 pi upon t, where t is the time period, and this is also equal to 2 pi f, because f is equal to 1 by t, and y is the displacement of the particle executing simple harmonic motion. So if I am able to write this equation in this form, then we can prove that the motion of this charged particle is simple harmonic along the axis of the ring. So what I will be doing is, I will be now writing this equation as a plus because q divided by 4 pi epsilon naught m r cube into x, which is equal to 0. Now if I compare this equation with this, so you can see here x is what? X is basically, it is the displacement, and here y is the displacement. So omega square, So this omega square will be equal to what? Q divided by 4 pi epsilon naught m dot into r cube. Now since this equation is comparable with this equation, this is the acceleration, A is the acceleration, and this term, this one, this is equal to omega square, and x is the displacement. So omega A plus omega square y is equal to 0. So here A, this is omega square, and this is the displacement. Okay, this is the displacement, and this is equal to 0. So both these two equations, so this equation is comparable to this equation of simple harmonic motion of a particle, and since both these equations are comparable with each other, therefore I can say that this negatively charged particle is executing a simple harmonic motion along the axis of the ring, and omega square will be equal to small q into capital Q divided by 4 pi epsilon naught into m into r, this capital R cube. And this omega is basically what? This is equal to 2 pi f. Omega, as I just told you, this is the angular velocity, which is equal to 2 pi upon t, and this is also equal to 2 pi f, where f is the frequency of oscillation. So first thing is that we have already proved that the motion of this charged particle is simple harmonic along the axis of the ring when it is released from the rest, because this equation is comparable to the equation of simple harmonic motion. Now, what will be the frequency? The frequency of oscillation will be equal to, now 2 pi f is equal to QQ divided by 4 pi epsilon naught m r cube. So the frequency of oscillation f will be equal to, and this is equal to what? This is equal to, this was equal to, this was the omega square, and omega square was equal to this much, and now omega is equal to, this is omega is equal to 2 pi upon t, so this will become 4 pi square f square. Yeah. So f will be equal to under root QQ divided by 4 pi epsilon naught m r cube, and this 4 pi square. It implies that the frequency of oscillation will be equal to 1 divided by 2 pi, because 4 pi square, the under root of 4 pi square will be equal to 2 pi, under root Q divided by 4 pi epsilon naught m r cube. So this is the answer. The frequency of oscillation of this charged particle along the axis of this ring when it is released from rest is equal to 1 divided by 2 pi under root of QQ divided by 4 pi epsilon naught into m into r, this capital R cube. So the motion is a simple harmonic motion, and we have also calculated the frequency of oscillation. So thank you very much for joining this session, and in the next session I will be coming up with a different topic, but the chapter will remain the same, that is electric charges and fields. So thank you very much. Have a nice day. Bye.